All right, we're still talking about introductory probability, and we haven't even gotten through all the rules. But after today, we'll have all of the main rules of basic probability that we work with. Now, today we're going to see the conditional probability formula. And so I've provided some notes. The first thing is our notation, this definition of a conditional probability. Some of the formulas that we use here, a lot of times you can solve these problems just by using the formula. So it's the probability of, here they say A given B, but if we use different letters like the probability of E, what's the probability that E occurs given that F has already occurred? Is how you would say this. So think about E and F as being two events that either occur in sequence, E then F, or you can think of them happening at the same time, but they're two different events. And the way we calculate this is the probability of E and F. And remember, and is the set operator that we use for and is the intersection divided by the probability of F. And I'll show you how this, this works in several problems that we do. If you solve algebraically for this numerator here, what you would do is you'd multiply both sides by the probability of F. And you can see that using algebra, that the probability of E and F, which is the intersection, is equal to the probability of F times the probability of E given F. So both of these two formulas are equivalent to one another. This one we call the conditional probability formula, but this one we call the product rule because it involves a product times. But they really are the same. And I will show you how they work by looking at probability trees. So let me show you how this works. First of all, we have two events, E and F, are independent. And independent, what that means is that knowledge of the outcome of the first event or the first trial gives you no information or doesn't change the probability of an event on the second operation that you do or event. So here's a tree diagram, and as the example, let's say that we're going to flip a coin and then roll a die. So our event E is flipping a coin, or our experiment, and let's identify a specific outcome. Let's say that we flip a coin and we get a head. Well, the probability that that would occur is 1/2. Let's also say that we roll a die and we get a 3. The probability of F getting a 3, well, there's 1 3 out of 6 rolls, like this. Now, we say that these two events are independent because let's say I flipped a coin and I got a head. And let me say the next thing I'm going to do is I'm going to roll that die. Does knowledge that I got a head on the coin toss, does that alter the probability of getting a 3 when I roll the die? Does it matter if I get a head or a tail first? Is it going to change the probability of getting a 3 away from 1/6? Or is it going to continue to be 1/6? All right, so the outcome of the coin has no impact whatsoever on the outcome of the die. We could flip a coin, 70 times and get heads every 70 times. The probability of getting a 3 is still going to be 1/6. All right, here's how the tree diagram would work. And I encourage you to draw tree diagrams for as many problems as you can in this section, 8.3. The probability, all right, so here's how a tree diagram is constructed. The first thing we're going to do, even though we could possibly take the coin in our hand and the die in the hand and just give them a toss and toss them both together. When we set this problem up, we're going to assume that they're done in sequence. We're going to flip the coin first, and then we're going to roll the die. Along the branches of the tree diagram, we're going to write the probability associated with each outcome. So the probability of getting a head is 1/2, and the probability of getting a tail is 1/2. All right, now we're going to look at our second outcome. Now we have 6 different outcomes when we roll a 3, but for the purposes of this, we're only interested in whether we get a 3 or something else. So here, so instead of writing 1, 2, 3, 4, 5, 6 and writing 1/6 next to each branch, what we're going to do is we're going to say if we roll the die, the probability of getting a 3 is 1/6, and the probability of getting something other than a 3 is 5/6. Well, we could get the 3 or a non-3 if we flip a head first or if we flip a tail first. The probabilities here are the same. Now, does the probability of getting a 3, does that change if we get a head versus if we get a tail? Are these going to change probability of getting a? They're not. They're the same. So knowledge of what the original coin toss was doesn't change the probability of getting a 3. If that happens, we say that these events are independent. Now, here's how you calculate probabilities in a tree diagram. You multiply along the paths, and then you say the probability of getting a head first and then a 3 second would be you multiply 1/2 times 1/6 to get 1/12. This one here would be the probability of getting a head and then not a 3 would be 1/2 times 5/6 or 5/12. And you can continue this way all the way down. The probability of a tail and a 3, well, you'd follow this path, 1/2 times 1/6, 1/12. And you can do this over and over and over again. So first of all, recognize that you can calculate compound probabilities, and that's the one that we're after, by just multiplying the probabilities along the probability tree. So it's going to be a good idea to actually construct these trees. In some cases, it's doubtful that you could actually even calculate the probability unless you have the tree. This one, you can do this problem, because the problem was what? What's the probability of getting a head and a 3? Well, we know what the experiment is. We're going to flip one coin, we're going to roll one die. We could actually write down all the outcomes. Here are the 12 outcomes. There they are. When you flip a coin and roll a die, those are the only 12 outcomes you have. So out of the 12 outcomes, how many of these are both head and 3? That one, just one. So 1/12. And notice that if we take the probability of heads and multiply it by the probability of getting a 3, the probability of a head is 1/2, the probability of a 3 is 1/6, and if we multiply those two together, we get 1/12. So use a tree diagram. It can help you solve lots of problems. And here's a scenario where we have 2 independent events. So this one here is the probability of A. We're trying to figure out the probability of A and B. That's the same thing as the probability of A intersect B. And basically all you have to do in the independent case is just multiply the probability of A times the probability of B. And because multiplication is involved, we call this the multiplication rule. But this one only works if A and B are independent, like flipping a coin and rolling a die. First of all, let me go ahead and give you just the generic case. So let's say we have A and A complement. Those 2 events are complements and mutually exclusive. And then we have B and B complement. Now, if you want the probability of A and B together, I've already mentioned that we're going to multiply going across here. So if we knew what this number was, and we knew what this number was, then we could multiply them together, and that product would be the probability of both things happening. All right, so let's get comfortable with identifying what these probabilities are. Along this branch, nothing happened beforehand, so this is just the probability of A. This one here, well, it's the probability of B but something has happened beforehand. A happened. So this here, and this here, and this and here, and this one, all of those after the first set of probabilities are called conditional probabilities. And the way we write it is the probability of B, and then this vertical line, given that A has already occurred. So this is a conditional probability. So if we wanted to multiply the probability of A and B, we would multiply by the probabilities along this path right here. And so it would be the probability of A times the probability of B, given that A has occurred. And this rule works regardless of whether A and B are independent or not. It always works. In the other case, we called this one just the probability of B because A and B were independent. In this case, we're not sure. They may or they may not be independent, and this works. All right, so let me try another one. A, B, C, D, C, D. So this one is the probability of A. Nothing has occurred before that. This one is the probability of B. Nothing has occurred before that first trial. All right, now this one here is the probability of C, but A has already occurred. So we're going to write this as a conditional probability. Okay, in the chat, what's this one? What probability goes along that branch? Question mark if you don't know. Okay, good. This one is the probability of, because we're going to D, it's the probability of D, but what has happened before that? A. So given that A has occurred. This one is the probability of C, because that's where we're going, given that B has occurred. And this one here is the probability of D, given that B. So all of these after the first branching of your tree diagram, everything that comes after that are conditional probabilities. Okay, so here's the one probability, probability of A and B, A intersect B. And you can see it's the probability of A multiplied by the probability of B given A. So it's the probability of A and B. It's the probability of A times the probability of B given A. So that's the first one. This works for all events A and B. And then down here, you have the probability of A and B, or the probability of A intersect A, B. Here, we're just going to multiply these two probabilities. Probability of A times the probability of B. But I mentioned that that only works if the two events are independent. So that's pretty much it in terms of formulas in here. We've got the conditional probability formula. We've got, here it is here again. Now they also say if you string along a bunch of events, it doesn't the probability for independent events doesn't apply to just two events only. You can actually string a bunch of events together and just apply the multiplication principle and just multiply all the probabilities together. All right, let's look at some problems here. All right, so you're familiar with this context. These notes are in the chat. A single card is drawn from the 52 cards. Well, maybe not drawn from the 52 cards, because in the problems for today, they're going to say, given that, and so you might be selecting only from the 12 or the 13 diamonds. You might only be selecting from the 12 face cards. So given that it is a heart, there are 13 hearts. So the context is that we're drawing one card out of the deck. But now we're saying, given that it is a heart, what's the probability that you're going to have an ace? Well, of these 13 cards we're drawing from, how many of them are aces? Just one. So we have one card out of 13, and that's the probability of the first one. Now, I can link this to our formulas if you like, and here it is. Let's say A card is an ace, and let's say H card is a heart. So if we were going to write this probability out here, we would write, what's the probability that the card is an ace, given that the card is a heart? Now, based on our probability rules, this is what we would say. This is the probability of ace and heart divided by the probability of a heart. So another way to say the numerator here is what's the probability of drawing the ace of hearts? Ace of hearts. Well, there's just one card out of the deck. That's the ace of hearts. So the probability of drawing the ace of hearts would be 1 out of 52. The probability of getting a heart when drawing out of the deck would be 13 out of 52. So if you simplify this complex fraction, multiply the top and bottom by 52, the 52s cancel, and you can see that we get the same probability if we use the formula. All right. So sometimes you can just intuitively reason them out, and other times you might want to go to the formula. All right. Let's take a look at 8. Given that it is a face card, so given the card is a face card, and the number of face cards we have is 12. So of those 12 cards, what's the probability that the card is red? So you can't say 26, right? Because now we're not selecting from all of the cards. We want to know just of those face cards. Okay, so number of red face cards is 6. So the probability of red given face card is red and face card, 6, face cards, 12. 1/2. All right, 8 and 10, it's nice to do 8 and 10 together because they just flip things around. 8 is the probability the card is red given that it's face card, and 10 is the probability it's face card given that it's red. How many cards are red? 26. Of those 26 red cards, how many are face cards? Jack of diamonds, queen of diamonds. That's right, 6. So given that it is red, the bottom number is 26. How many of those 26 cards are face cards? All right, so there's you know, a lot of others from this in this setting. It says here, find the conditional probability. So, you know, use a tree diagram if that helps, because conditional probabilities are in tree diagrams. Use this formula here, the conditional probability formula. That could be another tool that you use. Or sometimes you can just get the answer by reasoning it out. All right, so let's take a look at number 16. So this is that you're doing the fair coin, or the tossing 2 dice, and you're counting up the face of each of the 2 dice. So whenever you're doing a problem that involves 2 dice, even if it's a simple problem, it doesn't take long, but generate this table, because this table gives you all of the equally likely 36 outcomes when you roll 2 dice. First die is 1, second die is 1, sum is 2. And you quickly see what the pattern is here. These numbers in red are the different outcomes. We must count them all. The roll 1-4 is different than the roll 4-1. We have to count it twice because they're 2 different dice. All right, let's go back to the problems. The sum is 10. Okay, so we're not just going to go count up the 10s out of 36, because it says given that the roll is a double, and the doubles would be the 1-1, the 2-2, the 3-3, the 4-4, the 5-5, and the 6-6. So given that the roll is a double, that means there are 6 outcomes, so that's the bottom number. Out of those 6, how many of them give you a sum of 10? Sum of 2, sum of 4, sum of 6, sum of 8, sum of 10, sum of 12. Of the only 6 rolls that we're considering here, the doubles, how many of them have a sum of 10? Just the one. Here's the answer to number 16, 1/6. Let's flip it around. Given that the sum is 10, how many different outcomes do we have where the sum is 10? And of those, how many are doubles? That one is 4-6, 5-5, 6-4. 3 different ways that we can get a 10. How many of those are doubles? 1 of them, just the 5-5. So of the 3 ways that we can get a 10, the only one that's the double is the 5-5. The other 2 are not doubles. 6-4, 4-6, not doubles. All right, number 20. Do number 20. Number 20 says, the sum is odd given that at least one die is a 6. At least one die is a 6. Here's the grid. At least one is a 6. So you have to count two things. How many different rolls would there be at least one 6 rolled? And then of those that you just counted, how many of them have an odd sum? Odd in the mathematical sense, as opposed to even. Okay, now the only outcomes to answer this question, the only outcomes that involve a 6 are these 6, 7, 8, 9, 10, 11 outcomes. Don't want to count that one twice. This one has 2 6s. But there are 11 possible outcomes where you have at least one of the die is a 6. And they're on the outside here. So out of the 11, how many of them have an odd sum? So of these 11, let's count the odds. 1, 2, 3, 4, 5, 6. So there's 6 odd sums out of the 11 outcomes, the probability 6/11. Good, I see some answers in the chat there. All right, this next group of exercises gets you to think about the formulas. All right, so let's first write down some probabilities that we see here. What's the probability of C? All right, so you have events A, B, and C, and they're all mutually exclusive. And then you have events D, E, and F. So the probability of C, this is C with D, this is C with E, and this is C with F. This is C total number of C's. So the probability associated with C is 0.20. So if you consider all the C's together, then you look at the total. All right, what's the probability of E? Okay, you go to the row total, 0.40. All right, what's the probability of F and B? From the table, F and B intersect right there at 0.02. Okay, so you see how you interpret this grid here? Notice all of these are mutually exclusive. Here's one that's a little trickier. See if you can answer this one. E and F. All right, so for this one, it says that E and F are mutually exclusive, so they can't occur at the same time, so 0. In fact, this is our definition of mutually exclusive events. If two events have nothing in common, then their probability is 0. Okay, now that we can read the table, let's go ahead and calculate some of these conditional probabilities. What's the probability of E given C? I'm going to do it the first time just by kind of intuitive, and then I'm going to use the formula the second time. All right, the first time, I'm going to just kind of reason this out. This says the probability of E given that C has occurred. So given C, we're talking about those 20% down here. This is all of C. Given those, what proportion of it or what fraction of it or probability it corresponds to the probability of E given C. Now this one involves both E and C, so it's 0.07. 0.07 of the total 0.20 involves E. So if you want, you can convert that to a fraction. Now by formula, the probability of E given C is equal to the probability of E and C, this is E intersect C, divided by the probability of C. So if you use the formula, then this is what you would get. The probability of E and C is 0.07, and the probability of C is 0.20. See how we get the same thing? 7/20. On independence, if you want to tell if two events are independent, like flipping a coin and rolling a die, here's your test. This one says that the probability that A occurs given B occurs is equal to the probability of A. And what that means is that B has no impact whatsoever on what happened to A. So what's the probability of getting ahead given that we rolled a 3 on the die? Well, that's the same thing as the probability of ahead, because knowledge of what we got on the roll of the die does not influence the outcome on the head or on the coin toss. So you can think of this as the test for independence. So what you can do is you can calculate the probability of A given B, then calculate the probability of A, and if those two numbers are equal, then we say that the two events A and B are independent. All right, so to do one of these here, let's just look at 36. Let's calculate the probability of A, and then let's calculate the probability of A given E. Notice that the A comes first in the conditional probability. If these two numbers are the same, then we say those two events are independent. All right, so first, the probability of A, here it is. Probability of A without regard to anything else is the 0.70, just down at the bottom. And the probability of A given E, okay, so this one would be given E, so of this 0.40, what's the probability that we are at 0.28? So there's A and E divided by E. So here's the conditional probability. And guess what happens if you divide those two? You also get 0.7. So since the probability of A and the probability of A given E are both the same number, 0.70, we say that A and E are independent. There's your check. Let's calculate those two. Let's see if I can find another one. How about B and E? Probability of B and the probability of B given that E has occurred. Now, right there's the probability of B, 0.10, probability of B, the whole sum. The probability of B given E, so of the 0.40 of all of E, 0.05 of it is B. And this one works out to 0.125. And since 0.10 is not equal to 0.125, we say that B and E are not independent. Another way to say that is B and E are dependent. So this is the check that we use to determine if two events are independent. 0.7. Let's calculate a couple of these. See if you remember how to do these probabilities in a tree diagram. What's the probability of N intersect R? And here's the tree diagram. All right, now in our future problems, we're going to ask that you construct this tree diagram. You can see that well. There's decimal points in one of these. One thing that you should know about branching in a tree diagram is that at every branching, the probabilities must add up to 1. 0.2 and 0.8, 1. 0.4 and 0.6, 1. 0.3 and 0.7, 1. Every time you have a branching, the probabilities will add up to 1. Okay, what about this one here? Probability of N intersect R. So let's follow the path. Here's N, and here's R. So we're going to follow the path, and we're going to go this way. This works no matter if the events are independent or not. So we're just going to take the 0.7 and multiply by the 0.4, and that's going to give us 0.28, and there's your answer. All right, let's check out number 52. In 2 throws of a fair die, what is the probability that you'll get at least 5 on each throw? 2 throws of a fair die. Okay, so remember that the outcomes, we're not throwing 2 dice here, we're just throwing 1. And so here are our outcomes, 1, 2, 3, 4, 5, 6. At least 5 means a 5 or a 6. At least 5 on each throw. At least 5 on the first or the second. So this or here means you can get a 5 or more on the first throw, a 5 or more on the second throw, or possibly get a 5 or more on both throws. Tree diagram, at least 5. All right, so that means 5 or 6. And these outcomes here would be 1, 2, 3, or 4. Now we're going to do this twice. And so in building the tree diagram, we have to bring out another set of branches coming out of both of these here. So we've got the first toss and the second toss. At least 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So we can write the probabilities on each branch. 2, 6 here, 4, 6 there, 2, 6, 4, 6, 2, 6, 4, 6. Once we roll the die, we don't cover up one of the numbers and roll it again with only 5 outcomes. We roll it again with the same 6 outcomes. So these two rolls are independent. So if you then add up the 4 outcomes, I'll write it this way, the outcome and then this outcome right here, where you get at least a 5 and at least a 5, is 2, 6 times 2, 6, which is 1/9. I'm just going to go 5 and 5. If you do 5 and not a 5 or greater, then you have 2, 6 times 4, 6, which is, I guess you could cancel the 3 out of each one of these, or leaving a 3, so it's 9, but it's, what's that, 2 9s. Then we have not a 5, 6, and a 5, 6, and you would have 4, 6 times 2, 6, 2 9s again, and then not 5, 6, and not 5, 6, that would be 4, 6 times 4, 6, which is, now you probably don't have to do all of this, but we've got all the possible outcomes. So which of these outcomes are described in our event? Let's see, where are we? Here. At least 5 on the first or the second. So the only one that we're not going to count is this one right here. So if you add up all those, you get 5 9s. Every one of these outcomes has at least a 5 or greater. Here we have both 5 or 6s here. Here's a number 5 or 6 and a number that's not 5 or 6. Here's a number that's not 5 or 6. Here's a number that's 5 or 6. So we add those 3 up, and the only outcome we're not going to count is this one here, where we have none.